I think you should be more explicit here in step 2. We're learning about mathematical proof. So if you're a mathematician, this is hilarious, I have to say. So these two very studious looking guys here, so they're proving some concept in mathematics, and then they just say then a miracle occurs, because sometimes, how do you get from step A to step B? They did their best guess. And the joke being that obviously in math we can't do that. We have to be very deductive. We can only base anything we say based on some mathematical fact. Deductive reasoning, right? So this is when deductive reasoning gets hard. But let's look at proof. So we're going to actually be looking at how proofs work. We're going to do a little bit of review first. The thing about proofs is you need some rules. So we're going to give you some new rules. Here are some of the old rules. Ruler postulate. Remember that one? What was the ruler postulate? You guys remember what that thing was? You guys remember, Ali? He's way ahead. That's like Pythagorean theorem. This one was way basic. This was the one that basically says you can use a ruler to measure stuff. And how do you? So if you have a number line, right? So if this is x1 and this is x2, right? It says how do you find that length and take the absolute value of their difference? That's the ruler postulate. You can measure stuff with numbers. The segment addition postulate. Remember that thing? So if you have a segment and there's like a point between the other points, the measure of AB plus the measure of BC, the two smaller pieces add up to the larger piece. The protractor postulate was like the ruler postulate but for angles, and it says the way you measure an angle is you subtract kind of the two measures just like you would here. So if you had like an angle and you know this one was 60 degrees and you know that one was 30 degrees, then this would be 60 minus 30. So it's the same kind of idea. And then the angle addition postulate said if you have like adjacent angles, you don't necessarily have to be adjacent, but if you have two angles that make up, I guess it does have to be adjacent, that make up a bigger angle, then if this is angle 1 and this is angle 2, and this whole thing is angle 3, then the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3. So these are the postulates we know so far. Correct? Correct. So here's a whole batch more.
Whoa.
Yeah, whoa. But we've actually talked, I think, about all of these. I'm pretty sure we've talked about all of them. But now I'm giving it to you. So remember how postulates were, this is spelled wrong. Wow! Nobody ever told me that. It's postulate. So we know this. But because I'm now saying they're postulates, I can use them to prove other things. We're taking them now as facts. And a postulate is one that we're not going to prove. We're going to assume they're true. And again, we don't like to have too many of these, but we think these are obvious enough that if we don't prove them, we're probably not going to have a faulty kind of mathematical system. That's our hope. Yes, sir?
Would they call this a line with one convention that...
Well, we're using planar geometry. We're on a plane. Euclidean geometry. We're not going into some crazy places where some of this is not true. For some three-dimensional geometry, some of these may not be true. But we're looking at Euclidean geometry for this.
Oh, man.
So, I'm disappointing you. Through any 2 points, there exists exactly one and only one line, right? We talked about that. Now it's a postulate. If we needed to prove something else, we can use it. And then, conversely, a line contains at least 2 points, right? These are kind of an inverse and a addition and a converse. If two lines intersect, then their intersection is exactly only one point. So that's this situation. Through any of 3 non-collinear points, there's one plane, right? There's one piece of paper that can sit on top of those 3 points. And conversely, if you have a plane, then you must have at least 3 non-collinear points on it. So they kind of work together. If 2 points lie in a plane, so here's my plane, it's got 2 points on it. Well, that makes a line from one of the other postulates, but that line will also be on the plane. And if you have 2 planes that intersect, my drawings aren't so good. So one plane, another plane, I can't draw too well. But they intersect at a line, right? We know all these things, so now we have postulates to kind of document that. Now, you could call this postulate 5, postulate 6. You could use the number. I will tell you this, I don't remember their numbers. So if you're proving something, you say postulate 8, I'm not going to know what you're talking about. My strong advice is don't try to memorize the number that goes with it. Memorize the content. Okay? Yes? You forgot. Sorry. They'll come back. It always does. So anyway, we have to know the content of these. You don't have to memorize what number goes with which one. So let's see if we can figure out what postulate is illustrated here. So this one, I believe it's on the paper. Get this up here. So if this thing occurs, right, then this other thing, and it's hard to see what this like that. Here. So look at your list of postulates on your paper there. What is being illustrated here? Which one? Yes, sir. Postulate 7, and can you read that one for me?
If two lines intersect, then their intersection is exactly one and only one.
Excellent, right? So if two lines intersect, then they intersect at one and only one point. That is postulate 7. But if you were to tell me postulate 7, I'm going to be, what's that? I can't remember which number goes with which thing. So give me like the content that goes with it. How about this one? Yeah, Ellie? Yeah. So this was postulate 11. If two planes intersect, and I like that he just gave me the text of it. You don't have to remember necessarily as postulate 11, but you do have to remember the postulate itself. I think I've got a few others that may not be on the paper here. So let's see if we can figure these out just by looking up. You have a question?
What happens if a postulate is being wrong?
Oh, that's a bad thing, right? Our whole geometry system can fall apart. Every theorem or any other thing based on that postulate will no longer be true, and the whole thing collapses. So that would be bad. But if you look at these postulates, they're kind of obvious, right? I mean, so that was the goal. Let's see, we're making them very, very obvious to minimize the chance of that happening, which is why we don't like to have a lot of postulates, for that very reason. Yep. What? Not yet. In other words, we wouldn't be sitting here, right? We wouldn't have this geometry class. Yes?
If you take into account the time, you can prove postulate 8 incorrect.
You take into account the time?
Time is the fourth dimension.
I'm telling you, we're not in that dimension here. You can prove others, some of them are false also if you change your geometry. But if we're talking about a Euclidean planar geometry, where time is not a fourth dimension, then it's true. But you're right, if you change your condition. All right, what is this postulate here? What's going on? And look at your list of postulates and see which one it fits. Which one, Joseph? Right, that was postulate 6, right? A line contains at least 2 points. So if you have a line, you have at least 2 points. And then what about this thing here? Which one do you think that one is? What do you think? Yeah, that was postulate 8, right? Bring 3 non-collinear points. There's this one, right, great. And so it is kind of, it's stating obvious things. Somebody's whistling a lovely tune, but it also means you're not listening to me. Okay, what else I got here? I got some more. Oh, look at that. Which one's that? Oh, is it exactly the same one? Which one is this one? Which one's this one? Right, this one is postulate 5, so it's kind of like the converse of the other one. And then we've got one here. So which one is this one? We're looking at which got on your list there. You got it? Now what do you think, Kaya? Yeah, so a plane contains at least. So it all depends what you're starting with, right? What your conclusion's going to be. Very nice. Okay. So this one, we're going to use the diagram to write examples of postulates 9 and 10. So postulate 9 is a plane contains at least 3 natural linear points. So can we find, just from this picture, something that illustrates this particular postulate? So a plane contains at least 3 natural linear points. Amanda, what do you think?
I'd like to say two things. First of all, B, A, and C for the plane, because I know B and A are on the same line, but C is a set of non-collinear. And second of all, I mean, what if it was a three-dimensional thing and you had like one plane, like one point on the common downside, another one
Point on this plane?
another one
Point over
there,
here? Yeah.
and then third one.
Can you make a plane out of those 3 points?
Well, if it wasn't a three-dimensional, they were all kind of.
Well, we are in 3 dimensions. Yeah, so if you have a point on on this wall, one on the other wall, and one on the other wall, can you make a plane?
Yeah, but what if there was like one down here, one up there, and one?
Okay, can you make a plane? Yeah. See, that's what's cool about it. Any three non-collinear points, you can fit like a piece of paper on it. You know, and they may be sideways or diagonal, all different shapes. But yeah, that's what we write. It's true all the time, and you do have to think about them sometimes. And it's actually very smart to think about them because, as some of you said, if it's not true, then you know this whole geometry thing falls apart. So very smart to think about that. All right, what else we got? If postulate 10, if 2 points lie in a plane, then the line containing them lines out of plane. All right, so can we find a way to kind of show that in this diagram? What do you think, Joseph? So B and A lie in plane P. Okay, and so what? So what can we say? And it does, right? Yeah. So you've got 2 points here. That line will also be on the plane. So we're illustrating different postulates. That's all we're doing. All right? Yeah, that's not so bad. Okay. Now, assumptions, and we have, oh yeah.
Going back to that last postulate, which one is the
So that's not a line. Again, we're in Euclidean geometry, where we're working on a plane, and using Euclid's definition of a plane, then it's not going to curve. The line doesn't curve. If you're using a different geometry with a different shape, lines can be curved. And you're right, they start falling apart. So remember that we're just using our Euclidean geometry right now, but there are other geometries that can prove these postulates false or something anyway. Good thinking though. Alrighty, I do want to get back to assumptions. There was a little confusion, I think, on the last test about assumptions, and I thought we talked about it a little bit, so we're going to talk about it a little bit more, mostly for that reason. So what can we assume and what can't we assume when you're looking at a diagram? So I got a whole bunch of things you can assume, but let's see if we can come up with our own list before we look at what I came up with. So what can we assume looking at this? What can we assume? Yeah.
All the points are coplanar.
Okay, points are coplanar. Good. Like that one. Anything else we can assume? And there are some things that are going to be true in here. How about AD is a line? Can I assume that? Okay, so AD is a line in the plane, okay? Because I see it. I see 2 points. I see that line. Yes, that I don't have to. I don't need somebody telling me that. Yeah. Can we assume they are parallel? Great question. Julie said no.
because it doesn't have like usually parallel lines have it. They usually have a
They're
symbol.
a little symbol. We're told they're parallel, right? So are we being told they're parallel? So actually we can't assume that. I'm going to put that in the can't thing. That BF is parallel to CE. What else can't we assume about these 2 lines? You know what else we can't assume? We can't assume they intersect either. I can't assume they're parallel, and I can't assume they're not parallel. I don't know, I'm not told. Yeah.
I assume that they aren't perpendicular.
Which ones? B, F, and C, E. Can we assume they're perpendicular? What does perpendicular mean? Not per- I don't know. Can we? And so I'm going to say you can't necessarily. Remember, drawings aren't drawn to scale. So if these do intersect, who's to say? Right? So I can't assume perpendicularness on this for any of the lines. Can I? Because these ones kind of look it. You know, these ones don't look it. But, you know, what about AD and BF? Can I assume they're perpendicular? No. Can I assume they're not perpendicular? Not really. Jack?
You can assume that all the lines are congruent.
Can or cannot?
Can.
Well, lines are, because they're infinite, we don't really think of them as being congruent or not. But how about the segments? Are the segments congruent? Based on this? I can't assume that any of the segments are congruent. How about angles? Let's write it down here. Angle A. Oh, I need another point here, I'm gonna just put some other points in, if we didn't give me enough points. So I'm gonna look at that point of intersection, I'm gonna call that K, and I'm gonna call this one L. So angle AKB and angle AKB and angle B, I think that's H. Oh, I'm getting all confused, I'm looking, is that H, maybe that is H, okay. I'm sorry, I have a little trouble reading it. Let me try again. Are the angles, everybody's erasing too, I'm sorry. Angle AHF and angle BHJ. Let's see which ones I'm talking about here. AHF, BHJ. And I assume anything about those two angles? Yes. Why?
They're vertical.
They're vertical. So the first thing I'm gonna assume is that angle AHF, and angle BHJ are vertical angles. So I can assume that just because they look like two lines intersecting. You're allowed to assume that. And because they're vertical, that means they're congruent. So I do have some congruent angles on here, even without being told that they're congruent. I know they are because they're vertical angles. So again, things you can assume without being told. That's one of those things you can assume. I can assume the lines are intersecting. I can also assume, anything I could, let's see if you can figure that out here. CJD, angle CJD, and angle DJE. Can I make any assumptions about CJD, this one, and DJE, that one? Can I make any assumptions about those? Billy? They equal 180. What's another name for two angles adding up to 180? Which one's that? Which one's that one? So you got the right letter. Help her out there. Amy, what is that one? Supplementary. We can assume they are supplementary. We can also assume they are a linear pair. Right? So just by looking, you don't have to tell me that. I know this. But getting back to what can't we assume, I can't assume things like, if something was coming out of here, I can't assume complementary, because I don't know that's 90. So let's kind of look at the list that I wrote out here. So all points are coplanar. Angle AHB and BHD, I think that's over here, that's these two, are a linear pair. We've got other linear pairs that we can assume true just by looking at it. And because they're a linear pair, we can assume they are supplementary. AHF and BHD, those are vertical angles. You can assume that. It's okay if you see something crossing. You see intersecting lines. Yes, they are intersecting. And you have vertical angles. And you can look at collinear points that are actually on a line. AHJD are collinear. But what you can't assume are points that are not on a line. So GF and H, they may look like they're collinear, but I don't know that they are. So I can't assume these three are collinear, because it could be, it goes through two of them and it doesn't quite fit the other. That could happen. BF and CE, you cannot assume they intersect. They look like they might, but you also can't assume they don't intersect. BHA and CJA. So like these two angles, cannot assume they're congruent, even though they kind of look it. Can't assume that. And you can't assume the perpendicular, as some of them are 90, unless they give you the little box that says, if it came with this, yes, then you would assume that they are. So just things we can assume, things we can't assume, and don't go by what it looks like. If they gave you some weird, terrible picture, which is probably something I would draw, and they said, here, these are perpendicular. If they're telling you they are, even if it's a horrible picture. So we go by what we're told, not necessarily by what we see. Hopefully you don't get a terrible picture like that. So let's see, and I don't think I have this one on here. This is wrong. I don't think I have this one on your paper. So let's just do it from here. Just looking up. What statements can we assume to be true? So looking at that diagram, again, it's up on the board. I don't have it on your paper. Angle CEF and FED. CEF and FED are a linear pair, true or false? True, right? Because that you can do by looks. It's a straight line with a line going through. How about CEF is congruent to that one, to FED? Can we assume they're congruent? No, right? We don't know. How about the length of CD, that's this, is the same as the length of BD?
Yes.
Yes? How come?
It's above lines and segment.
Well, it doesn't say they're lines. It says the length of the
Oh,
segment CD
segments.
equals the length of the segment BD. So no, right? How would you know they were? If they put a little congruence marker, then you could say they are, but they didn't. Lines FG and CD intersect at E. True or false? Yeah, you could assume that's true. Angle CEF, and GED are vertical angles. What? Where'd they go?
What?
Everybody watching this is almost like they must have all left the room. I don't know what happened. Are they vertical angles? Loud and proud. Yeah, Joseph. Yes. I don't know where everybody went. And then FG, this one, and BD do not intersect.
That would be so.
That would be false, right? This is another way of saying they're parallel. Nope, I don't know. Does not say. Maybe way out in space somewhere they will fit. I don't know. So, very good. Yes, ma'am. What? False is, can you prove it's always true? If it's true, like, is this definitely true? Yes, it is. Is this maybe true? Sometimes, if you're interested, sometimes it might be. Then you can't assume it is true. But sometimes it isn't. So false kind of wins. Right? And doesn't that make sense? It could be that they are, but I don't have any information to assume they are. All right, let's sketch some diagrams. I'm on page 2 here. So sketching diagrams, so important. You will find me saying over and over again, "Oh, I can't do this. Did you sketch a diagram?" No. Call me back when you sketch a diagram. This is so visual. Geometry is so visual. There are people who can think in their heads. I don't know how you do it. You must draw pictures. So sketch a diagram showing line TV intersecting segment PQ, all right, at point W, so that segment TW is congruent to segment WV. So like, how do you do this? Like, so you start with TV. I'm gonna make a TV. So you have 2 points on there. TV. Then what can you do? You're gonna want to draw point W as a midpoint. And actually, you know what? These are blah blah blah. You know what I do? I say, okay, look, I've got 2 intersecting segments and lines, whatever I got going here. So let me make them intersect. And I know they intersect at point W. That's what it says. And now it says TW is congruent to WV. Right now, this does not tell me that. So I'm going to put a little congruence marker, TW and WV. Now I have said it. So if you get a diagram and it has these little markers on it, then you can assume congruence once you see those little markers. Yeah.
What if, like, there are 2 congruent lines? Like, how do you tell that? Say UW is congruent to WP. How do you tell that? It's
In addition to this one,
Yeah.
you would make 2 little markers. Yeah, that's an excellent question. Because sometimes more things are congruent but not all to the same thing. So at a glance, I can look at this picture and I know what's congruent to what. That's an awesome question. Yes?
If you have like an enormous diagram, do you keep it like you have like 20 little markers on the line?
You could. They can get complicated. But I'm doing this is like picture's worth 1,000 words, right? You know, you've heard that expression. It totally is. Trying to read this, look at these words and look at what you get. Isn't this a lot more simpler? That is not good English. Isn't this more simple? Isn't this simpler? Yeah. So the picture, it makes it so much clearer. If you're having trouble and you haven't drawn a picture, don't ask anybody yet for help. You draw that picture. Draw the picture. It will probably answer your question. This diagram I don't think I have on your paper, but let's see if we can do it. Sketch a diagram showing AB intersecting CD, these lines intersecting each other at point E, so that the 2 lines are perpendicular. This whole thing means perpendicular if you haven't seen that before. So I'm going to make, go ahead, try it. I'm going to make mine, you make yours. Let's see if we can make it the same thing. Find a little space on there to do this. Huh? Can you use a what? If you want to.
Are those arrows in there?
Well, it says line AB. Well, yeah, here's my segment. Okay, draw your own. Let's see if we match. Draw your own.
Where?
Find a little white space or take empty out a piece of paper if you don't find any room. I think those are segments here. I guess I shouldn't put them on. That's okay. Okay. Let's see if we meet. If you're just copying mine, I want you to kind of think about it. Like, how would you draw these diagrams? Oh, practice our use of the E. Okay. There we go. So, how did you do? How did I do? Now, if you notice, like, the answer, right, and I put that in quotation marks, because the one that I drew is slightly different. And you see in the D, I named like in different ways. So is this one not correct? No. There may be more than one way to draw a correct drawing. But this represents that, and this does too. Hopefully yours does as well. Alrighty. Perpendicular figures. Alright, so now we move on to the next little topic here. You can only assume a line is perpendicular. And again, this is the little symbol for perpendicular to another line or plane if it's stated or marked with a right angle symbol on the diagram. That's that little box. So we're looking at this kind of 3D figure here. It might be easier to look on the board because it's colored to actually see the 3D-ness of it. Which of the following statements are definitely true? So maybe that gets back to what Amy, you were asking before. They're definitely true. It's true all the time based on the figure. So A, B, and F, these points, A, B, and F are collinear. Is that definitely true? What?
So instead of being true and false, it's more like definitely true and possibly false.
We're saying, can you assume it? So that's a yes, no, true, false kind of thing. Can you assume it? Yes. Yes. Look, they're all the same line. Yes. We get very nervous. I don't know. Oh, yeah, yes, yeah. E, B, and D. E, B, and D are collinear. Can I assume that based on what you're showing me? What are you trying? Why not? You said no. Well, I know 2 points will make a line, right? Do I necessarily know that it's going to hit this third one? No. I don't know that. Let's see. AB, where's AB? Here it is perpendicular to plane S, which is kind of the reddish colored plane. So this perpendicular to that piece of paper. It's got a pencil poking through to that red piece of paper. Perpendicular. What do you say? Yes. How come? Yeah, we have there's a little marker right here that says it's a right angle. So yup. Yes, you can. What else we got? CD is perpendicular to plane T. Where is CD? CD perpendicular to T. What do you say? So here's the pencil poking out of the blue piece of paper. Perpendicular? What do you think? What do you think?
Well, it sort of is.
Sort of is? What do you think, Joseph? It doesn't have a right angle side, so, in that sense you can say no, but do we have enough information from this one? Hard to say, right, because this one, I know that one's perpendicular and it lines in that plane, and this one's is on the other plane that is perpendicular. I don't know, this one I think might be true. Hard to say. Why? I don't know, isn't it? Because it's on this plane, so if I know this line, oh yeah, no, it doesn't have to be. Yeah, it doesn't have to be. Right, does not have to be. There was one that for some reason didn't make it on my chart, but it's on your paper. AF intersects line BC at point B. Okay, so here's AF intersects BC at point B. What do you say? I think that's true, right? Mm-hmm. Yeah. I think we got that one. Alright, so couple of U-tries here. Just take a couple minutes to do these U-tries. We'll talk about them. Well, let's see if we agree here. So what I got for these, For any 2 points, there's one and only one line, right? And a plane contains at least 3 non-collinear points. Do you agree with that? And let's see, here's my diagram. So I've got XY intersecting VW at T such that they're perpendicular, right? So it should have something like that. Now, it may not be exactly like that, but it could still be correct. And then it says the WT, segment WT have to be congruent to segment TV. This one and this one. Do they have to be congruent? No. It doesn't say. Like you might have drawn it like this, and you could still be correct. Right? This is still correct interpretation of this. So it doesn't necessarily mean it's right in the middle just because they're intersecting. Now look what I got here. Here's my true, true, false, 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 true. How do we match? And if not, do we have questions? Because sometimes they're a little bit hard to see. So where are we not agreeing? And let's see. It could be me too. I could have made a mistake. Convince me otherwise.
I agree.
You agree with me? Yes.
I have a question about the JK lies and
This one? Okay, so let's see. Here's JK, and here is plane X. So is that line in that plane? Yes. It's also in the other plane, but it's in both of them. That was that line of intersection. Yeah.
So a line L is different than LJ.
Yes. Any 2 points on that line you can use to make. Okay, any other ones we're just a little fuzzy on? Please ask if you have any questions. Okay, all right. All this was just kind of stuff to help us get back into first. Just little facts we kind of have to have. Now this I know you had to do because we did this in the warm-up. How to justify steps. And this is a proof. Like we did this last year, but it is a proof. Every statement you make, you give a reason. So this is my given statement. So you usually, but not always, you start with what they tell you. What are the facts you're given as truth? So we're given that this thing over here equals -1. And so the next step would be this. Now, how do I get from here to here? What do I do? Go from here to here. Like that. We left again. Oh, Abby, what happened? Distributed property, right? We distributed this guy. All right, the next step I have in my equation solving is I got here. How did I get there? How did I get there? Right here. Here, Joseph. Basically, 14x is minus 3x is 11x. Well, now I'm getting this statement. How did I get from here to here? Huh? Yeah, we don't. So then it should be easy. I don't know why nobody's answering. Oh, yeah. So, well, how do I get from here to here? You don't even need to look on the paper. We should know this. Yes? How do I get there, Abby? Okay, subtracting 21 from both sides. And then I got here by division property of equality, right? You divide both sides by 11. Right? This is what we practiced in the warm. This is what you did in Algebra 1. You were doing a 2-column proof. You didn't realize that. So we're going to look at proofs now that are not algebraic proofs, but are more like geometry proofs. So here's generally what proofs look like in geometry. They give you stuff, here it is, and then they ask you to prove something. That's what they want you to prove. If they don't give you a picture, you draw it, but this one they're giving you a picture. They're saying segment AB is congruent to segment CD. And they gave you the little congruence marker. If they hadn't given you the congruence marker, you put it in. So your first step is you mark up the diagram based on your givens. Before you do anything, you kind of have to figure it out. So let's see, this thing congruent to that thing, they want us to show that AC is congruent to BD. Now just think about it. Does that make sense? That these whole things are going to be congruent? Now, just can we say it in words how we know that's going to happen? Why? What do you think, Amy? Yeah. So this piece is congruent to itself, right? So you're kind of adding congruent pieces. So we can logically see it. Now let's see how do we formally write it down. So you start with your givens here, and again, this one's written down, so you can just kind of look up here and think about it. So this is my given statement. So I say given. Now I have to kind of start thinking about things. So I'm going to say the measure of AC is the measure of AB plus the measure of BC. Who says I can say that? Second addition postulate, that's all that is, right? My next statement is BD is BC plus CD. Who says I can say that? Yeah, Amanda?
Second addition postulate.
There it is, I'm using it twice. Great. Now let's see what happens here. I'm saying AB plus BC, not this thing, equals this thing plus that thing. You know what, I think I need a 3A. I kind of wish there was another step here. That might make this a little easier to see. I'm going to change this statement to read AC equals BC plus CD. Now what? AC, is that one? Oh, wait a second, no. Never mind. AB, okay, never mind. Well, I'm just thinking of a different one. All right, so let me see here. From here to here, what happened? AB plus BC equals CD plus BC. Well, that's this thing, right?
I don't understand.
Well, it's basically saying this one equals that one, and let's see if we can figure out why. Oh, okay, I see what happened. Okay, never mind. I'm coming back. You know what, when I went to school, we would write these all ourselves. I think it's more difficult when they give you the statement, you have to come up with the reason. You know what happened? You see how AB equals CD, isn't that this statement? You see that part? And what do we do to both sides? We added BC to both sides. Who says I can add BC to both sides? Addition, property of equality. So, alright, I see it. Then what? AC equals BD. Now where'd that come from? Where'd that come from? Yeah? AB plus BC is the same as AC. That's this statement, right? CD plus BC, that's this one, is the same as BD. We put that here. So that is substitution property. Anybody's mind explode?
I have my anti-mind going.
Okay, well that's good. So it's like, you have to think like, what? Like that. So something that you can kind of simply see, and then listen, there may be other ways to prove these things. There may be other ways. But this one I'm using, this is our postulate, this is our properties. These are all mathematical facts to get there. Let's try another one. Maybe we'll do this one a little bit better. Okay, this one, bottom of page 3. So the measure of, these are my givens here. Measure of angle 1 equals measure of angle 3. Now they marked my diagram. I'm one of these people, I kind of have to mark it myself, just it makes it in my brain a little better. Determine whether the measure of angle EBA, that's this piece, is the same as DBC. This piece, what do you think? Why?
Because one's rear than the other, so it's basically saying,
And we're kind of adding same thing to same thing. It looks to me like, we might see a little bit of addition postulate on here, but we'll see, maybe or not. We'll see how we do it. And they're giving me the statement. So, who says measure angle 1 is measure angle 3? Yeah. That's a given. They told me. Okay. Let's see what happens. EBA. EBA is the measure of angle 3 plus angle 2. Who says I can do that? Yeah. Joseph? That's not what you have to. This is angle addition postulate. Says if you have two little ones, it adds up to the big one. So that would be the angle addition postulate. Or we better just sure of it, right? So that one says if you add two pieces, you get the big angle. Let's see what this one says now. It says measure of angle EBA equals measure of angle 1 plus measure of angle 2. Now I'm looking, what changed between statement 2 and statement 3? What changed here? What changed? What changed, Jack?
The measure of angle 1 is the measure of angle 2.
Yeah, angle 3 turned into an angle 1. Well, what? How come I can do that? How come I can do that? they are congruent, right, or equal. So I'm gonna use the substitution property of equality, right? Because this equals that, then I can substitute that in, no problem. That's what the substitution property says. I'm like, okay, who's with me so far? One person, awesome. Okay. So let's see what they're telling us next. Measure of angle 1 plus the measure of angle 2 equals the measure of DBC. This plus this equals that whole big thing. Who says? What's that thing called, Joseph? Angle addition postulate. You remembered it now, right? You're adding two pieces to get the big one. That's the angle addition postulate. Let's see, where are we going from here? Oh. We're getting to our conclusion, right? This is our conclusion. I got there. How'd I get there? Well, what happened? You see it? Joseph, what happened here? Uh-huh. Isn't that the transitive property? If A equals B and B equals C, then A equals C, right? That's the transitive property. Right, that's transitivity. So look at this one, equals that one. Here it is repeated, right? So there's some equal, therefore those are equal. Make sense? And this is going to take a little bit of, you're going to have to wrap your brain around a little bit. Let's see, I got to work them. Oh, yes. So let's see what's going on with this one. So there's a picture here, and it says the measure of WY equals the measure of XZ. Now, they didn't mark the diagram, so you do it. So WY, well, let's see, that's this big thing. That is going to be congruent to this big thing. So find a way to kind of see it there. And what are we trying to prove? This little piece WX is the same length as that little piece WZ. Let's see if we can figure this out. So we've got our given. And now I'm saying WY equals WX plus XY. WX plus XY. WY equals the little piece plus this little piece. Who says? You add two pieces of the segment, you get the whole segment. Who says? This is more than just knowing this. What is that? This plus this equals whole thing. What's that one? Segment addition postulate. If you have two pieces and you add them together, you'll get the whole thing. Alright, then it says XZ equals XY plus YZ. This big segment equals these small segments added together. Who says? Yeah, I think exactly. Again, we're just adding little pieces to get a big one. Then some magic's going to happen.
Then a miracle happens.
Right? You're saying, well, then a miracle happens. Yes. WX plus XY equals XY plus YZ. These two things are equal, is what it's claiming. How come? And this is the place where maybe I want to do another step. So see this XZ? And XZ is the same as WY. So can I replace this? I'm adding another little step here to make this a little easier to see. If I insert this here, how do I get from here to here? Right, that is substitution, isn't it? Substitution property of equality. Because WY and XZ are the same thing, so instead of writing XZ, I'm writing WY. And let's see if that helps us see why these two things are equal. Now I've kind of got the transitive property of equality. If this equals this, WY, and if WY equals this other thing, then these two things are equal by the transitive property of equality. All right, we're dutifully copying it down. That's good. But are there questions where this came from? It's just a kind of a new way of thinking, very logically, very step by step. Yes, sir.
So our
You know what, they're almost interchangeable, I wanna say almost, like, I could have said substitution here, because that's as well, because it really is, I'm kind of substituting equals for equals. So, very often I will take either one. And then let's see, how did I get from here? So I went from this statement to that statement. Well, what disappeared? The xy's are gone, right? Okay, wx equals yz. How can I get rid of those xy's? I'm gonna just subtract them out, right? Who says I can do that? The subtraction property of equality. Really? Really? So, a lot of thinking going on here. Or is there? It turns it off. Turn it back on. Yes? There's a slight difference because sometimes you can use transitivity. The real reason is transitivity. I think substitution kind of works, but sometimes it's true substitution, not transitivity. So it's kind of like if you say substitution, you're probably not wrong. But you might be wrong if you say transitivity sometimes. I mean, this is transitivity. If A equals B and B equals C, then A equals C. If that's not a situation you have, then you can't use transitivity. But substitution kind of means, transitivity is like a special case of substitution. Listen, if you can get that far, I'm really impressed. All right, I have one more example here. Let's see if we can get this one working here. I'm hoping, like, as you see more of them, you're starting to notice, oh, this is how I have to think about it. So let's see. Given measure of angle 1 equals measure of angle 4, you go to your picture. I know it's marked, but it helps me to sometimes just like, okay, just by kind of putting my pencil there, right? Those two things are equal. The measure of angle EHF is 90. Now I know they put the little box here. I'm just kind of going over it. Okay, that one's 90. It draws my attention to it. GHF is also 90. All right, well that makes sense, right? Because it's a linear pair. I get that. Now what do I want to show? I want to show that this angle and this angle have the same measures, 2 and 3. And so it helps to kind of logically think about it, right? These are equal, and they're both 90-degree angles here. It kind of makes sense that if these are equal and you subtract them from 90, you get the same number on both sides. So you kind of have to convince yourself, yeah, okay, I see it. Now let's see formal proof. How would you do that? So my first statement are all the givens. I'm just putting them out there. You don't always have to do that first, but you know, it's not wrong to do that. Then I'm saying the measure of EHF equals the measure of GHF. Why can I say that? Why can I say that? Are you in the protractor? No?
They're using the measures of the angles.
You're saying these, okay, you want to build on that, Keely, a little bit? Substitution, because they're both 90 degrees, right? So I'm going to say transitive, but substitution is not wrong. This is kind of a very clear transitive case, because this equals that, and that equals this, so these two things are equal. Substitution is correct as well, I wouldn't mark it wrong. But this is a case of transitive, just to kind of show you, it is. But substitution, I'm okay with it, I really am. All right, fantastic. Now they're claiming that EHF is the measure of angle 1 and the measure of angle 2 added together. This plus this gave me the whole thing. Angle addition postulate. You're adding two angles to get the whole thing. Alright. Angle, the measure of angle GHF is the measure of angle 3 plus the measure of angle 4. So this whole big one equals these two pieces added together. Who says? Yeah? Same thing, right?
But also, couldn't it also be substitution, DHF and DHF, and then.
But do I know these two are equal yet? I don't know that yet. Okay, but I like the way you're thinking. I like that you're looking and you're like, it could be this. I like it, you're getting it. I'm happy. If you're not happy, you didn't get the right answer, but I am happy and you're thinking about it. Okay, now what? Now we're kind of getting to the conclusion of what you wanted to happen beforehand. I'm saying this one this set, 1 plus 2 equals that set. And, they're making a little bit of a leap here. I'm gonna try and insert a little, like a 4A here. I'm gonna say, I'm gonna take this and replace it with measure of angle EHF. And that's all I'm gonna change. Now, why can I do that? I just change this one to that one. How come I can do that? Look up here. We've already established that these two have the same measure, right? So that is substitution. I'm just substituting in. I'm substituting in EHF wherever I see a GHF. And that might make the next step a little bit clearer. Because if you look at step 3 and my new step, EHF is 1 plus 2, and EHF is 3 plus 4. So what can I say about these two things? They have to be equal because of, well, substitution is here. Because of the, it's okay to have substitution there, but it is really the transitive property of equality. So they were kind of combining two things because they said they were substitution, but it's kind of the transitive property. It's two little things happening. Yeah.
Well, I think we just say angle 1 plus angle 2 equals EHF, and angle 3 plus angle 4 equals GHF, therefore angle 2 equals angle 3.
You're skipping steps. Like, how'd you get from there to there? Well, because that equals that, and then, so your mind does that like this. But now we're backing it up and saying, wait a second, how'd you make that leap? So you have to break it down into the intermediary steps that I have reasons to prove something. So it's like slowing your brain down a little bit, or it's not even slowing it down so much as organizing it. Organizing the brain. Like, we've always let it run rampant, which is a good thing, to get an overall picture, but you have to be able to kind of back it up with facts. All right, I know these are simple ones, but if you think about something more complex, you really want to break it down into little pieces that you can prove. All right, now it's got a blank here. It says you're going to use the substitution property of equality to come up with something here. What do you think? Okay, so you're going to say, you're going to put the measure of angle 4 here. Well, I want 2 to equal 3, right? So something has to happen here. But what do I know about the measure of angle? So you're going to change this one. You can do that. You want to say the measure of angle 4 plus the measure of angle 2 equals the measure. Is this what you're saying? Well, I can't get there yet until I do this, right? So what he did was he said 1 and 4 are the same. That's a given, right? So I'm using substitution. You could have changed it here as well. I think I said the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 plus the measure of angle 1. Either way, right? So either substitute here or substitute here. Because now I see the same angle. And now I can subtract it out to get here. Subtraction property of equality, like, holy cow. Are you kidding me? Are we have to be able to do all this? Yeah. Who gets it? Yeah, I'm like, okay, that's pretty good. So, I mean, is this a new way of thinking? Absolutely. It's like you said, because I know, like you've got a lot of really sharp people in here. Jack, really sharp. We've got a lot of really sharp people in here. That we don't stop and think about it. We just kind of know. So now we're saying, wait, back it up. How'd you get there? How'd you get there? What were the intermediate steps that got you there? And that's how you prove kind of big things, by breaking them down into smaller things. Okay, awesome. That's it. I don't know why that was extra. So here we go, introduction of proofs.